for the chapter 8. Okay? So we looked at the acid-base characteristics of alcohols. Okay? If we've got our alcohol, how do we know it can act as an acid or a base? Okay? Well, here's an example alcohol. What's the name of this alcohol? How many carbons are in the structure? 2 carbons, meaning we've got eth. Do we have any double bonds? No, so it's ethan. We've got an alcohol, so it's ethanol. Okay? You should be able to look at that structure and start to identify things that are reactive about it. Where's our reactivity going to be centralized? Around the oxygen. Why around the oxygen? I can accept that. I like a more general answer for it. Oxygen is electronegative. So while it has electrons, it's also electronegative. So it's got electrons that it can then do stuff with, but then it's also drawing electron density in the bonds that it's attached to towards it as well. That's going to further increase our possible reactions, because what happens to the atoms then attached to it? What happens to, say, this hydrogen? It becomes partially positive because we've drawn electron density away. What happens to this carbon? Same thing, partially positive. Okay? Our oxygen attracted all those electrons and it's partially negative. Okay? Now that we've got those partial charges, we can start to apply our definitions to those. If we look at Bronsted-Lowry, the Bronsted-Lowry definition, you should immediately think about what? Protons. The Bronsted-Lowry definition focused on protons, or hydrogen ions, which means we're going to be looking at, for our first case, the hydrogen. Okay? That hydrogen is partially positive. To become a proton, that's a hydrogen ion or a hydrogen atom that lost an electron. What charge does a hydrogen atom that's lost an electron?
Positive.
Positive. We're becoming a proton right now. That is a partially positive atom, which means reactivity as far as that hydrogen is what? Bronsted-Lowry acid. It's starting to look like a proton that can leave that structure. Okay? What about our oxygen? It's got a bunch of electron density. Sorry, terrible arrow. Could we put more hydrogens onto that oxygen? Yeah. Which means we can look at oxygen as a proton acceptor. What's a proton acceptor? First part of that is our proton, so we're looking at a Bronsted-Lowry, and if it's a proton acceptor, it's a base. Okay? We've washed out or taken care of all of our Bronsted-Lowry definitions, so now we can move into our Lewis definitions. Okay, our Lewis definitions on our electrophile and nucleophile. Okay? Lewis said protons sucked and looked instead at electrons. So we now have to go through this structure and find out where we have electrons. Where do we have electrons? On the oxygen. Remember, it's partially negative. Okay? So we could now look at that as a Lewis definition. What can it do with those electrons? It could donate them. If it can donate them, it becomes a Lewis base. Okay? Lewis base is the same thing as... No, don't do that. A nucleophile. Okay? It's attracted to positive charges. A nucleus is positively charged. So our Lewis base is also a nucleophile. Okay? What else do we have in here? Do we have another partial charge? Yeah. We've got our partial charge on that carbon. Okay? So what could that partially charged carbon do? Can it act as a Bronsted-Lowry acid? No, why not? Because carbon is not hydrogen. Okay? So we can ignore our Bronsted-Lowry definition. Okay, so let's move to Lewis. If it's positively charged, how could I stabilize it? I could add electrons to it, making it a Lewis acid. What's a Lewis acid? It's also an electrophile. Okay? So looking at that reactivity allows us to see what can potentially occur. We now have an idea of what's going on with it. How would we decide what it is actually going to act as? React it. We have to give it something else to react with. Okay? So if we drew in another species, we could then start to evaluate how that compound is reacting. Okay? And that's what we did with our acid-base characteristics. We looked at it briefly with our substitution. We also looked at it with our elimination. Okay? So let's go through a couple substitution and elimination reactions just to see what's going on with that. If we look at a substitution reaction, let's, not do a double bond. Let's pick this guy. If we wanted to run a substitution, we'd have to substitute what in this structure? We'd substitute for our oxygen. The bond that's going to break in our substitution is going to be between the carbon and oxygen. Why not between the hydrogen and oxygen? What reaction would that be? Looking at the transfer of hydrogen ions, which is Bronsted-Lowry acid and base. Okay? So when we move to substitution, we're not looking at the Bronsted-Lowry definition, which means we have to ignore that bond. That's not the one that's going to be changing. So if we're going to do our substitution, we need to substitute that OH group for something else. What charge is on that carbon? That carbon right there. Why is it partially positive? Because the oxygen's more electronegative. You're getting tired of saying electronegativity yet? Yes, okay, maybe I'll stop asking it. We'll see what happens. Okay? So if that's partially positive, how can I stabilize it? I need to bring in a species with electrons. Okay, so if I'm going to do a substitution reaction, whatever I add has to have electrons. What's a good species that has a lot of electrons? Could look at oxygen, it's the same thing. Any of our halogens. So we could pick something like chloride, okay, with a negative charge. And we could look at that chloride coming in and doing a substitution. However, what's the byproduct of that? This bond breaks, forming OH minus. Is that a stable leaving group? No, which means we wouldn't get our reaction. So we have to somehow facilitate that bond breaking. How can we facilitate it breaking? We need to make that oxygen less negative. What we're going to want to do is also add a hydrogen atom, something else that's nice and positive, okay, to neutralize some of that electron density on the oxygen so that it can become more reactive. And so in our very first step, we're going to end up putting on a hydrogen onto that oxygen. The oxygen is now positive. Does it want to be positive? Nope. So now we're facilitating, we're forcing that oxygen to take the electron density away from that carbon. That carbon becomes positive. How can we stabilize that carbon? That's where our chloride can come into play. Okay? And our final result, after a series of steps, would give us with our substitution. Okay? With water as the other product. Okay? So all we're trying to do is follow the chemistry, follow to see what happens. Okay? I know that takes some practice, but that's why you do it. Okay? What happens if we change the circumstances around now? Instead of it being chloride, I'm going to pick something like, let's go with SO4 minus 2. Okay? We'll draw out our intermediate product at the end of this too. So we can have our oxygen take the electrons away. We end up with what charge on that carbon? What charge is that carbon? Positively charged. Okay. What mechanism would this be running based on? 1 or 2 type? Unimolecular, bimolecular? Unimolecular. Why? We see a carbocation. Don't focus on the on intermediate steps, because when we look at the alcohol chemistry, we have to have an intermediate. That very first step, that isn't, whoops, that's an eraser. That is an intermediate. Okay, which has to happen regardless if it's SN1 or SN2. Okay, so don't focus on an intermediate, focus on the carbocation intermediate. Okay, so we're looking at a 1 type because of that cation. Okay, if we've got sulfate as our negative charge floating around, yes, that's negative, but is that a good nucleophile?
No.
No. And that's because that structure has resonance. The negative charge, in fact, both negative charges in sulfate bounce around through that entire structure, meaning that negative charge is virtually useless as far as our chemistry goes, which means we don't have a nucleophile. If we don't have a nucleophile, can we do a substitution reaction? At least as far as we're concerned. No, because it's S what? 1, but what's in the middle? N for nucleophile. If we get rid of the nucleophile, we can't do that substitution reaction. Okay? So we still have that unstable structure. We need to find electrons somewhere within it. Where are there electrons in that structure?
Carbon.
In the carbons. Where else? Looking for every possible answer here. In the carbons. Where else are there electrons? There's electrons in the bonds. I kind of want to dodge away from hydrogens, because where's the electron that hydrogen brings in? In the bond between it and carbon. Okay? So we've got electrons in the bonds, and we've got electrons on individual carbon atoms. Okay? Is carbon going to be willing to give up its individual electrons? No. So we're going to have to move to the bonds. Now the question is, what bond do we try and get electrons from? Do we try and get it from a carbon-carbon bond, where they're 100% equally shared, or do we try and get it from a carbon-hydrogen bond, where the electronegativities, while being very similar, are not the same? We'll go from the carbon-hydrogen. It's a polar bond. Okay? That's going to be easier access to those electrons. It's then a question of which hydrogen do we go for. The other name for our elimination reactions is, I know someone already said it. We'll talk about that too in a second. It's again an eraser. Let's try that again. B for beta elimination. Where's the alpha position? It's where our cation is. So we'll move 1 atom further away. What's the next letter in our alphabet? Beta. So we'll move to that carbon and say, okay, what hydrogens are attached to it? Where do we have polar bonds? So we can go through and we'll see that we've got 3 possible options. Okay. Yes, I'm only drawing 1 hydrogen on each of those, even though each of those carbons has more than 1 hydrogen. Okay. All of those bonds have electrons. All of those are potential sources of electrons. Okay. How do I decide which one to take electrons from? This is another thing that gets a lot of students frustrated. Draw every single bloody product. Okay? I don't care how long it takes. Draw every single one out. Until you guarantee that you get the right answer every single time, you're going to draw it out, which means I'm going to make you do it. I'm going to do it too. So if we take a look to our structure to the far right, if we remove that hydrogen, we're going to take the electrons away from the hydrogen. Come on. We're going to move those Seriously. Stupid eraser. We're going to take the electrons from that bond and move them towards the carbocation. In the process, what are we going to form?
Double bond?
A double bond. We end up with that as our structure. As we continue to move, what is that, counterclockwise around. I can't touch anything right on the screen right now. Okay, so we move to that upper hydrogen. What we're going to do is take the electrons out of that bond and move them towards our carbocation, forming a double bond. What's our product look like? Now it looks like that one. If we look at the last hydrogen, we're going to take our electrons out of that bond, move it towards our cation. We're going to form
double bond?
Good answer. We're going to form another double bond. So we end up with 3 possible products. Okay? Of those 3 products, we have to decide, are they all of equal energy? Okay? Which means, do they all have the same reactivity? Okay? What makes each of those structures reactive? Which is what we're going to move into when we deal with chapter 4 and 5. The pi bond. Those electrons are held further away from the atoms. Those are reactive electrons. So if I want to look at those structures and see their ability to react, I want to see how easy it is for those electrons to come out and react with something. So what we'll do is evaluate what things it has to get around, what things are preventing those electrons from getting out. And when we take a look at our structure, let's say up here, we've got 1, 2, 3 non-hydrogen things preventing those electrons from moving out. What happens when we move to the second structure? We only have 2 things preventing it. Which one is more reactive?
The one in the middle.
The one in the middle. If it's more reactive, are we going to be able to form that? No. So that product's eliminated from our possible answer. If we move to the last one, we look again at the things around our double bond. We've got 3. That's the same as our first one. So we've got 2 possible products. Yes or no? They're the same thing, which means no, we don't have 2 possible products. They're exactly the same. We've only got 1 product. Okay? How do you know they're exactly the same? Well, that's chapter 6. Was that the chirality one, right? Yeah, our stereochemistry chapter. You pick up those structures, pick up the one on the right, pick it up and flip it over, superimposes directly on top. So we've got same molecular formula and superimposable, meaning identical. Yes?
Can you go over how they're not escaping? I don't really get the...
So let me draw it in a slightly different situation here. If we take a look at this double bond versus this one. What's the difference between those 2 structures? No difference? Exactly the same?
Oh, no, they're obviously different.
Okay. That's what I'm asking. What's the difference?
What's carbon and hydrogen?
What's the difference between carbon and hydrogen?
Electron.
Exactly right. So in our bottom structure, there's a lot more electrons there. We're looking at the reactivity of that double bond. The double bond is a source of electrons. So if we're going to look at that bond's ability to react with something else, we have to take those electrons and bring them out of the structure. So what we're looking at trying to do is bring the electrons out in either case. If we look at our bottom case, we try and bring the electrons out this direction. I know we run into the bottom of the screen, but what else do we run into? Run into a carbon. If we do that same situation over here, carbon versus hydrogen, you said carbon has more electrons. What happens when we get those 2 electrons near each other? They repel, and the electrons that try to go out come right back in. Okay? Whereas in the upper case, they can go by the hydrogen. Okay? So when we're looking at double bonds, The more substituted, the more non-hydrogen things attached to it, the less reactive it becomes, because we're burying the electron density in that double bond inside the structure. We're preventing it from getting out. Does that make sense? Okay, and that's why we end up seeing our products favoring on the other side. We see, we see that as our major product and not this one. Okay, so what we go through and do is draw on, or you could draw on, all of the extra atoms attached to those double bonds. And the one that we've got crossed out, what atom is attached up here? What atom is this? Let's try that. Carbon. How many bonds are shown to it? 2. How many bonds does a carbon need to have? 4. So what does that mean? 2 implied hydrogens. So what atom's out here? Hydrogen. What atom's over here? Hydrogen. Hydrogen is not a non-hydrogen atom, so we won't count that as a substituent. We'll only count these 2. What atom is this? Carbon. How do you know it's a carbon? It's a point. Okay? And as we defined earlier on, every point is a carbon atom unless otherwise labeled. Okay? So in this case, we've got only 2 things that are not hydrogens attached to our double bond. Whereas up here, what do we have? We have 3. That makes this double bond less reactive, a more stable product. It's going to be the one that's going to form in the largest amount. Yes. Okay. Questions about your substitution, elimination, acid base with alcohols? Okay. So what we can do is then go on and move on from there. Okay. There are alternate substitution reagents. So if we wanted to look at, let's go through and draw this out. I want to start with, say, this structure, this alcohol, and I want to turn it into this alkyl halide. Sorry, those electrons look a bit gimpy. Okay. What reagent could I add to facilitate this? Don't tell me SOCl2. What kind of acid? You're right, because we need the acid to activate our alcohol, and then what else? What else has to be there? We'll need our hydrogen to activate our alcohol, and then we also need the chloride. So the acid that we'll add would be HCl. Okay? That would work to facilitate this substitution. Okay? But let's say we don't like the reactivity there. Okay? So what we can do is go through and change our chemistry around, and what we'll do is add SOCl2 instead. Okay? Your textbook kind of explains this, I'm not positive, but maybe it does. Our structure for SOCl2 looks like this guy. It's an awful lot of stuff to just add a Cl. So what's going on in this case? So what we can go through and do is again investigate the reactivity of each of our atoms. We've already looked at our alcohol reactivity, so let's look at the reactivity of SOCl2. What can you tell me about those chlorines? A lot of electrons. They're electronegative, right? So what charge would they build? We're looking at partial negatives, right? What can you tell me about that oxygen? Also partially negative because more electronegative than sulfur. So what can you tell me about that sulfur? How positive do you think it is?
70%.
Pretty positive. Why do you say pretty positive? Because it's not ugly, right? Got at least one laugh. That's all I need. Okay? Chlorine, chlorine, oxygen. 3 very electronegative elements attached to 1. What does that mean about that sulfur? It is extremely positive. Okay? If it's extremely positive and it's not a hydrogen, what could it act as? So now we got to go back to our 6 definitions. So I said not a hydrogen, so it's not Bronsted-Lowry. We're looking at Lewis. Okay, what Lewis? Is it Lewis acid, Lewis base? Lewis acid. Okay. What makes it a Lewis acid? It's partially positive. One of the reasons why we don't run with the Lewis acid definitions is because it's not as easy to remember your negatives and positives. If it's a Lewis acid, it's also a electron acceptor or an electrophile. Okay, what do electrophiles react with? Nucleophiles. Okay, an electrophile is something that wants electrons. So what do I need to find in my alcohol? Electrons. Do we have electrons in the alcohol? Absolutely. So what ends up happening? Our oxygen shares its electrons with that sulfur. Okay? This is where I don't want you to be too concerned about the mechanism. Which bond is the easiest bond to break in there? The pi bond is actually the weakest. Okay, you're right. So what we can do is break that pi bond. Okay, and we end up with a new product. What's that product look like? Sorry, requires a lot of drawing. Okay. Sulfur started partially positive because it had a lot of electronegative elements attached to it, right? How partially positive is it now? Probably even more. Why? There's another electronegative element attached to it, and that electronegative element happens to be positively charged. So it's probably even more positive. So what's it going to do? It's going to steal electrons. Where's its best source of electrons right now? Why the oxygen, not the chlorines? The oxygen's negatively charged, and we would typically classify it as less electronegative, right? Chlorine's not going to just give up its electrons. But now sulfur has too many bonds, so what happens? We're going to have to kick somebody out. What's a nice easy one to kick out? Our chlorine. Okay? This is where the mechanism gets really, really gross, and I don't expect you to know this part of it. That chlorine is going to take the electrons, and it's going to immediately share those electrons with anything that's positive. Okay? We do have a formal positive charge on that oxygen, but is that oxygen really positive? No. So it's drawing the electron density from all of the atoms around it, particularly the hydrogen and that carbon. Okay? So really, where's our best source of positive? Either the hydrogen or the carbon. Ultimately, what do we want to do? We want to form a bond between the chloride and the carbon. How do we know that? Because we've got it drawn right there in the product. Okay? Make life easier at first. Then you can make it more difficult later. So what's going to end up happening in this case, and like I said, it's a tricky mechanism, the chloride electrons in that bond are going to come out and attack the carbon. At the same time, it kicks out the oxygen. Okay? And what ends up happening as a result of that, the only part that I expect you to know, you've done your substitution. Okay? This mechanism is not strictly correct, so don't get too bogged down in the exact electron motions of it. It's not one I expect you to remember. I'm drawing it up here so you can get the idea of what's happening and what has to be occurring in this process. Okay? One of the side effects of this result is that we get our substitution. And also, because it all happens at the same time in this simple step, what happens? It's an SN2, but it's really weird for an SN2. SN2, what happens to stereocenters? Inversion. what do we end up getting in the case of SOCl2? Retention.
Rhymes with attention.
What? So we get retention of stereochemistry. Okay, it's one of the only reagents that will allow you to do this. It's really, really rare. Okay, but it does happen to occur here. Will I expect you to remember that? Probably not. I do expect you to realize that SOCl2 will allow for a substitution where you're swapping out an alcohol for a chloride. Okay? Make sense? Getting the idea of where it's coming from?
I'm
Yes.
confused. Why is the chlorine sharing with the carbon?
So it's pretty much all coming down to the best analysis that I've actually spent doing on it is with this sulfur. That sulfur is a group 3, or not group 3, in period 3. It's expanded its size, and it's gotten close enough to the d orbitals that it can expand its octet. And so what ends up happening is you get some weird electron transfers within the structure, allowing for very rapid kicking off of this portion of the group. This is now an exceptional leaving group, while at the same time the sulfur wants to get rid of the chloride. So as that leaves, the chloride comes off and immediately comes back in that exact same spot. Okay.
Show the sulfur as one of the products? Like how would that work?
That compound is highly unstable, and if we wanted to look at the product for that, if I remember correctly, you get sulfur dioxide gas. One of the reasons why this reagent sucks. Anybody know what sulfur dioxide gas smells like? Not pleasant. And HCl. Okay, so those two products are also formed. Why am I not as concerned that you guys remember those two reagents as products? What class was this? It's organic chemistry. Organic chemistry is looking at carbons and hydrogens. Do either of those two products have carbons and hydrogens in them? One of them has hydrogen, but it doesn't have the carbon. Okay, they aren't organic products. Okay, it's a bad habit of mine, but I'll continue to do it throughout the semester, is start to get rid of or ignore the non-organic products. Okay, because it's organic chemistry, we're focused only on those products. Okay, questions about SOCl2? Okay, so the next part of Chapter 8 looked at some reduction and oxidation reactions. Okay. And just so you guys know, I will post these slides with better drawings showing each of these reactions this weekend. I just haven't had time to do it yet. And I'll also post the lecture audio and all that too. And I did get Thursdays finally up. Sorry. Okay, so we're looking at oxidation reduction reactions. Okay. According to general chemistry, what we looked at was loss of electrons is oxidation, gain of electrons is reduction. How would you remember that? Oil rig, which I personally don't like, but that's me, I guess. Leo says, Gur, why do you think I like that one? Or any hints why I might like that one? Not a bad connection, but no. I wasn't allowed to have sugar when I was growing up. Which is actually true. Very deprived childhood. Yeah, it was rough. How do you spell Leo? Any ideas how you might spell Gur? Close enough. Okay? That's one of the reasons why I haven't remembered it, just stuck in my head. Okay? And that's how I've got it set up. Okay? Which is why that's how I'll end up writing this out. Okay? You'll also notice that if you ever had general chemistry from me, I don't ever remember those. And particularly when students ask me, oh, is this one oxidation? Leo says, Leo, loss, electrons, oxidation. Okay? Remember, the whole memory thing doesn't work so well for me, so I've got to go through and eventually derive each of these things. Okay? So that was Gen Chem. That was nice. We could come up with a nice symbol or term that we could put together to have it memorized. Unfortunately, organic chemistry, not quite so nice as far as our memorization goes. Okay? And what we've got to do is look at our reactive site. Okay? It's typically going to be a single carbon atom, and we're going to look at the difference. What happens to it as we go from our reactant to our product? If we decrease the number of hydrogen bonds attached to it, okay, we're looking at an oxidation. Also along those lines, if we increase the number of electronegative bonds, okay, those usually go hand in hand. If we decrease one, we've got to increase the other, okay, for oxidation reactions. Both of those would be classifications for oxidation. For reduction, we're looking at the opposite. Okay, if you remember from Gen Chem, your reduction and oxidation go hand in hand. If one goes up, another species has to go down. So if we look at our reduction, if we increase the number of hydrogen bonds, we're looking at a reduction. If we decrease the number of electronegative bonds, we're looking at a reduction. Okay, why the terms oxidation and reduction? Oxidizing, okay, is our common term, which is a reactant or a species reacting with oxygen. So if we looked at, say, a combustion reaction, we're taking some carbon and hydrogen containing compound and we react it with oxygen. What's our product? It's the product of every combustion reaction.
Water, CO2.
We get CO2 and water. What happened to the number of bonds, hydrogen bonds, around that carbon? They decreased. So we're looking at an oxidation. What happened to the number of electronegative bonds? Is oxygen more electronegative than carbon? Yeah. How many electronegative bonds were formed in that process or broken? We formed two, technically actually four, electronegative bonds. So we've increased them. We're looking at an oxidation. Again, where's the oxidation come from? What happens? We added oxygens. So in most cases, when we're looking at oxidation reactions, we're looking at increasing not so much the number of electronegative bonds, but the number of oxygens. Okay? So as we increase the number of oxygens, we're oxidizing our structure. What happens if we remove oxygen from the structure? We're ultimately looking at a reduction. Okay? It's not quite as simple as that. We do have to evaluate the electronegativities, but it's pretty close. Okay? So let's see, do I have this set up right? Yep, we'll look at some examples. Okay? Like I said, I didn't have time to draw structures, so I just had to put up some formulas. Or not even formulas, just functional groups. Let's take a look at, kind of nervous about doing this one, but we'll do it anyway. An alkane to an alkyl halide. So let's pick ethane. And I'm going to do the reaction where our alkane becomes an alkyl halide. How would I draw my product to make it look like an alkyl halide? I need to add a halogen. I'm not trying to be tricky yet. Actually, I don't think I'm ever intentionally trying to be tricky. Sometimes I'm just stupid that way. Okay? What happened in this reaction? Like I said, this one's a little bit trickier as far as I'm concerned. I'm not positive on this one. Okay? We've lost a hydrogen to our carbon, and we've added an electronegative element. Okay? So to me, I believe this is actually an oxidation reaction. We've increased the number of electronegative elements attached to our carbon. Okay? It's a much rarer case. You guys won't ever see this reaction. Okay, we've looked at alkyl halides, we looked at alkanes. How many reactions have I shown you where we've produced those? We haven't looked at this reaction. Okay, and that's because that chemistry is not easy. So we can move on, try a different one. Let's look at an alkene. So an alkene, again, we're going to try and aim simple. We'll go with ethene. and we're going to turn this into a dibromo compound. What do you think? Oxidation or reduction? Okay. We've definitely added bromines to this, but what happened to our hybridization? It's also changed. Okay? What we've done here is we started with an electronegative bond. What happened when we shifted? We lost that electronegative bond, and then we formed it. What's the net result? Nothing. Okay? So this is neither an oxidation or a reduction. Okay? It's a trickier one. Okay? Because we see those electronegative elements show up, so we would immediately jump on those, but you have to remember that your sp2 carbon is effectively larger in electronegativity. Why is it more electronegative than an sp3 carbon? All the way back. Tighter electron density around the carbon because it's less hybridized. It has more s character in those orbitals. Okay? More s character, the electrons are held tighter. Okay? So we get, sorry, I meant to write that, neither. Let's try another one. Let's try our alkane. So we'll start with our methane again, and we're going to take this to an alcohol. Did I just call that methane or ethane? Sorry, ethane. Okay, what happened now? What happened to that hydrogen attached to that carbon? Did it stay there? This carbon has 3 hydrogens attached to it. How many hydrogens does that carbon have now? 2. So what happened to the number of hydrogens to our carbon? It lost a hydrogen. And it gained an oxygen. What type of reaction did we do here? We did an oxidation. Sorry, I was trying to color code. That failed. I'll just make it 3D now. You're just not wearing the right glasses. Okay. What happens? Let's try, what do I want to do this time? Let's go with this. We're going to start with this functional group, which is carboxylic acid, and I'm going to take it to this functional group, which is an alcohol. What happened in this reaction? We lost oxygen bonds, so we're looking at a reduction. Okay? Kind of get the general idea on what's happening? Okay, so let's see how we can actually do some of these reactions. So what we're going to start with is with our alcohols. I don't expect you to be able to start with an alkane and move that to an alcohol. I'll always ask you to start with the alcohol and see what can happen to it. So we're going to start with, in general, we're just going to start with, come on. How could you classify this alcohol? Methanol could. How else? We don't necessarily know it's methanol because I haven't specified what those bonds are. Actually, I need to specify what those bonds are. Let's make those hydrogens. So methanol, let's not do methanol. I get lied. Change my mind again. Let's make it this structure. So we call it ethanol, but move beyond that. I don't want ethanol. classify it? Primary. How do we know it's primary? We're looking at our carbon where our alcohol is attached. That carbon is only attached to one other carbon. It's primary. Okay, so what we're going to do is start with the generic reaction here. We're going to go through and do an oxidation. We're going to ignore the reagent for the moment, but we want to put something there so that we know we're doing an oxidation. Okay, so what we can do is say, well, for an oxidation reaction, we're increasing the number of bonds to oxygen, or decreasing our hydrogen bonds. So we can put oxygen as a reagent. We'll put it in brackets. So whatever our reagent is, it has to supply oxygen. Okay? So our first step, we're going to increase the number of oxygen bonds. We're going to also have to decrease the number of hydrogen bonds to that carbon. So we can draw on our CH3 again. Nothing's going to change to that. Let's get rid of one of those hydrogens. Stupid. Should get a muffler for the audio. Okay, we're going to get rid of one of those hydrogens. In this case, I'm going to say we're going to get rid of this hydrogen. Okay, attached to that carbon. And we want to increase the number of oxygen bonds. How could we do that? Okay, we could try and do something like this, right? Is that what you're suggesting? Okay, we've increased the number of oxygen bonds. That sounds reasonable. Except, oxygen, don't draw that, by the way. Sorry. Oxygen is extremely electronegative. Okay, that's going to really upset that carbon. So that carbon's going to get upset and try and drag electrons back as best as possible. So this structure is actually highly unstable. Okay, so we end up not forming the diol on a single carbon. What we're going to do is form the double bond to oxygen. Oxygen then has too many bonds to be happy, so we'll erase that hydrogen as well. And what do we have? We formed a carbonyl. Okay, or carbon-oxygen double bond. What functional group is this? Carbonyl is our class, not necessarily a functional group. Label it a little bit better than that. It's not an alkene. An alkene would be double bonds between carbons. It's an aldehyde. Okay? Do we still have more hydrogens on that carbon? Yeah. So what could we do? We can do another oxidation reaction. Okay? And so now what we're going to end up doing, same general idea. We're going to get rid of that hydrogen and form another oxygen bond. Okay, so now this hydrogen is gone. Okay, can I form that triple bond to that oxygen? No, that's not a really happy thing. So what are we going to have to do? We're going to have to add another oxygen. Is oxygen happy on its own? So what are we going to do? We'll give it a hydrogen. What functional group do we have now? Carboxylic. Is that right? Okay, I'll trust you. We've got a carboxylic acid. Okay, so if we start with a primary alcohol, we can oxidize that all the way down to the acid. Okay, given the right materials. If we just oxidize the crap out of it. Okay? What happens if instead of being a primary alcohol, though, we start with, say, this alcohol? What kind of alcohol is that one? Good call on the isopropanol. That would be the name. But what I was looking for was a secondary alcohol. Okay, so we could draw on, sorry, I didn't do a very good job drawing that. Let me try that again. We got a CH3 out there. Wow, it's not getting any better. CH3 there. We're going to go through and try and oxidize this. Okay, do we have a hydrogen that we could remove from that carbon? Yep, so what are we going to do? We'll remove that hydrogen. And in the process, what do we need to do? We need to add a second bond to our oxygen. What functional group have we formed? Now we have a ketone. What? Yes. Okay. Well, we went ahead and oxidized it the first time, so let's oxidize it again. Do we have any hydrogens attached to that carbon now? No. Can we oxidize it again? If we start with a secondary alcohol, we can't oxidize any further. We can only do one oxidation step. Okay, so it stops after that first oxidation, regardless of how strong our oxidizing agent is, that we can control at least.
In the first step, how are we assuming that it's going to lose that hydrogen?
I haven't talked about that. We're saying that this is an oxidation reaction. We have to get rid of the hydrogen so that we can form another bond to the oxygen. So when we do an oxidation reaction, we have to increase the number of oxygen bonds to an individual carbon. Okay, well, if we add another bond to that oxygen, that carbon would then have too many bonds, so we'll break the next easiest bond, which would be our hydrogen.
So where does the oxygen, as far as the reagent, come in?
Here, that's going to facilitate breaking this bond.
Okay.
Okay? What's happening? Oxygen has electrons. Where do those electrons go? They're going to have to go towards the carbon to form our double bond. Which means, what happens to these electrons? Carbon would have how many electrons if we move those electrons down and in? Ooh, I didn't bring a pen.
Give it 5 bonds.
Give it 5 bonds. So carbon has too many electrons. So what do we have to do? We have to kick electrons out. Where do our electrons go? Towards this hydrogen. Meaning we form hydride, or H-. How stable is that? Not stable at all. Okay? So our reagent has to facilitate the transfer of those electrons, and it's going to happen through a transition metal. Okay? And we'll look at that in sort of a second. Okay? I again, don't want to get too bogged down in the details with it. Okay? One of the unfortunate things with the redox reactions, the mechanisms behind those are a little bit more complex than I want to deal with, and I don't want you guys to worry about those. What you're going to have to do with our redox reagents is memorize them. Thankfully, there's only 2 that you have to worry about. Okay? Other questions about these 2 systems before we erase all of this? Okay, so our lesson, primary alcohol, we can oxidize to an aldehyde and a carboxylic acid. Secondary alcohol, we can oxidize to a ketone, and it stops at the ketone. Is there another type of alcohol I could draw? We could look at a tertiary alcohol. So let's go ahead and see what happens if I've got a tertiary alcohol and I try and oxidize it. If I'm going to go through and oxidize this, what do I have to be able to remove from our center carbon? A hydrogen. Do I have a hydrogen there? No. What happens? No reaction happens with our tertiary alcohols. Okay? So with our oxidizing agents, when we discuss what those reagents are not going to react with our tertiary alcohols. We don't have to worry about those. Okay? So you're only concerned about your primary and secondary alcohols. So the next part is actually looking at the reagents, okay, or what chemicals we're using in this case. Our primary reagent that's going to be of any real concern is chromic acid. There's a variety of sources of chromic acid. We're looking, that was the wrong button, looking at H2CrO3, okay, is chromic acid. We can get that, like I said, from all sorts of different places. The most common one that your book seems to show, potassium dichromate. H2SO4, and I think they say heat. Okay? So if you see either of those two reagents, chromic acid or dichromate with sulfuric acid, those are referring to the same thing. Okay? They're going to function the exact same. Okay? The chromium ion there happens to be +6, I believe. Has anybody heard of +6 chromium? You've seen, was it Erin Brockovich? Yeah. What chemical was she concerned about? Chromium-6. Okay. It's extremely reactive. It's extremely dangerous. And for one of those reasons, is one of the biggest reasons why it's so reactive, is it oxidizes everything it sees. Okay? So if that gets ingested, it pretty much oxidizes your DNA, does all sorts of messed up things. Okay? So we want to avoid that reagent as best as possible, but since it's here, we'll go ahead and evaluate it. What the structure ends up coming down to, so if we take a look at our alcohol, got our hydrogen, here's our carbon with our other hydrogen, chromium oxide. Okay, pretty much have this. What can you tell me about that chromium in the middle? Why is it positive? A lot of electronegative elements. Take it a step further. Where is chromium on the periodic table? It's a transition metal, which means what charge? Positive. Our chromium atom is extremely positive. What does that do for us? If we've got a positive atom, how can we stabilize it? We can give it some electrons. So our oxygen can share electrons with it. Whoa, what was that about? Okay, and we end up with another structure in between. Okay, we got this guy. Our oxygen's not happy with that hydrogen because it's positively charged. So what happens to the hydrogen? It takes the electrons away from the hydrogen, and we get rid of our positive charge, and we end up with this structure. Okay, negative charges all the way around this now. Okay, not a particularly happy structure to be in. Okay. We said we had to form the double bond. Okay, and one of the things that we were looking at was having oxygen share its electrons in. But if we did that, we had to kick off H-. Do we have anything right now to stabilize a minus charge? No, if anything, we don't have any electron, or we don't have anything to stabilize a minus. We have things to make it more unstable. So instead of kicking off H-, what about H+? Do I have something to stabilize positively charged hydrogen? Yeah, I've got all of these oxygens. So what I can do is take that hydrogen as an H+, which means what happens to the electrons in this bond? They go to the carbon. Okay, so the carbon could be negative. Chromium over here, really, really positive, not happy about it. So what's it start to do? Pulling electrons like crazy. So what happens to the electrons in this bond? They're starting to pull towards the chromium. But then what happened to your oxygen? The oxygens become electron deficient, so it wants electrons. So what happens? Our electrons from that bond back on our hydrogen, stop doing that, go to form our double bond. What happens to the bond between our oxygen and our chromium? Those electrons go towards our chromium. What's the net result of all of that? A whole mess. Yeah, that works. I can accept that. But that's only because I drew it with my finger. We've got our carbon-oxygen double bond. So we've done our oxidation. And then we've got our chromium species now with more electrons. So it's a little bit happier. It's changed its oxidation state because it's now gained electrons. That H plus comes over, ends up reacting over here. That chromium species can now go through a series of other reactions, kicking off water eventually, and you end up with chromium, I think, dioxide. Okay? What you need to realize is that your chromium or that chromate reagent is extremely reactive. Okay? And it's going to oxidize and remove any of these hydrogens that it can get a hold of. Okay? Any hydrogens attached to that carbon. And it's going to replace them with oxygen bonds. Okay? You get a slightly different version of that when you move to the aldehyde. Okay? Because then your aldehyde carbon is positive. So the chromium oxygen comes in, does a substitution, or plays around in a slightly different transition state, but you end up again increasing the number of oxygens. Okay? And like I said, a similar type mechanism. Okay? So what are you ultimately responsible for here? Let's see if I put in my blank. Yes, I did. No, I didn't. I just went backwards. You're responsible for realizing that our chromic acid, or CrO3, or as we said already, our dichromate, okay, is an uber oxidant. Yes, I said uber, and I decided to write it too. Deal with it.
Way to be committed.
But I said oxidant, not oxidation. Uber oxidizes, or ox. Okay, I'm tired of spelling. Okay, it's like babe. Okay, except it's in black, not blue. So if we start with a primary alcohol and we add chromic acid, what would we expect our product to be? It's an oxidation reaction, but what functional group does our product stop at? Remember, chromic acid is an uber oxidant. If there's any hydrogens available on that carbon, it's going to convert them into oxygens. An aldehyde has a hydrogen there. Okay? So if we add chromic acid to a primary alcohol, we will convert it all the way to the carboxylic acid. Okay? It does not stop at the aldehyde. But what if you want the aldehyde? If that's your target goal, it would be nice to have a reagent that would allow us to do that. Okay? So we need something a little bit milder, maybe a little bit more polite, maybe something a little bit more PC. So what reagent do we use? PC, chromic acid. Politically correct chromic acid. I think it works pretty well. What does that mean? We'll do a single oxidation. Okay? It cannot go to the carboxylic acid. So what happens if you take an aldehyde and you add PCC to it? Nothing. Okay? What does the PC actually stand for? Once I tell you, you'll actually like the politically correct better. Pyridinium chloro. Okay? What we've done is change the acidic conditions. We've made them slightly basic. That changes the reactivity. It slows it down. It prevents that last step. Okay? So if you see PCC, that's how I'll write it on the test. The other way you might see it is pyridinium chlorochromate. I'm going to take my best guess at what that looks like for the structure. Nitrogen. Chloride, and then your chromic acid. Okay? So instead of having sulfuric acid, you have the pyridinium ion, which is this guy. And then you've got the chloride to balance it out. So you get your pyridinium chloro and then chromic acid. Okay? Those are your redox reactions and your substitution reactions. The homework that I assigned that's due Thursday has you practice those. So you'll look at primary alcohol reactivity, secondary alcohol reactivity, and then also do some stuff with the thionyl chloride.
What about the quiz?
The quiz, that is due Tuesday. You can get help from whoever you want except me on anything that says perfect next to it. Okay? I don't care who you talk to, you can find the most genius person on the planet. Okay? Go online, scan it, copy it, do whatever you want as long as you get the answers 100% perfect. You will receive credit for those. When it comes to questions 7, 8, and 9, I'll help you with those if you've got questions. Those should look really familiar, particularly if you decide to start the homework.
So you want us to use our tests and do
Use whatever you want. This quiz is due Tuesday. Yes. That's good.
So pretty much like
Do we really not have any more extra?
so these right on the exam plus whatever extra you added.
Sorry, I was thinking about other stuff. What were you saying?
So on these questions where we got it correct and they want to send it over and let it ask
Are there really no extra quizzes? You got an extra one? Okay.
I missed one.